Hey everybody, today we will do another quick video, and we will do another circuit in the area of using the techniques of the cases involving the transient and all those, but we're not doing too much transients. We're just basically doing analysis based on the information that we got. But so let's start with a problem. It says find IT in the circuit in figure 810. Find I of t. Find I of t in the circuit in the circuit in figure 8.10, right? So assume that the circuit has reached steady state at t is equal to 0. Assume that the circuit has reached steady state at t is equal to 0. Okay, so basically now what does the figure say? Well, the figure says the following. So I got a voltage source of 10 volts, and then I got resistor of 4 ohms, and then I have a capacitor, and then we have an inductor. I believe it's an inductor. No, actually a resistor over here. It's a resistor. And then we have an inductor. But before that we had another resistor. So we have another resistor. And then we have an inductor. And then we have, right? So, and I believe that this resistor is 6 ohms. And I believe that this is 3 ohms. And I believe this capacitor is 0.02 farads. 0.02 farads. And then the inductor is 0.5 henries. 0.5 henry, right? So that is the information that was given to us, right? So now let's try to analyze this. Now, before you get to the switch, I think after you get to passing the switch, passing the resistor, we have a switch. Passing the resistor, we have a switch like this. And then we have an arrow going like this. Like this. That means that this was, at some point, it was closed, right? At some point it was closed, but then somebody opened it. Somebody opened it, like when you turn the lights off and you open the switch. Actually, when you turn the light switch off, you opening the circuit. So somebody went and flipped the switch. Now the switch is open, but at this time right here, at t equals 0, so nothing has happened yet. At that instant time, that when time is equal to 0, the circuit is still in a steady state, which mean that this is acting like it's energized. And when this is acting like it's full energized, this is still in a steady state, which mean that this capacitor is like an open circuit. It's like nothing is going over here. When this guy is full of charge, it's acting like a voltage source. It's seeing like this, like, okay, so I'm like, it's like I am looking at you, I am the same as you. He's looking at this guy like I am the same as you right now, I have the same value. So it's like nothing, right? It's like nothing over here between this and this. So in other words, we can actually get rid of this for the steady state, and we can say that 10 volts, right, is right here, but nothing is happening, right? Nothing is happening right here. So technically we have just something like this, right? And then we have, actually no, it's just a resistor at the moment right here. And then we have, and I believe that, so technically it's, and then this is acting like a charge, so we don't have to worry about that. So technically we have something like this. So 6 and 4. That is basically when this is steady, at the moment with steady state. Now, what is going on over here now, then, right? That's the question. So now, in this case, right, so 10 volts, we can actually use what is called the current divider rule, or the voltage divider rule, to get the current, right? So basically what we can say is that at t equals 0, we can say that the current I of t, right? But okay, so I of t, okay, is equal to what? Is equal to V, right? Over, you can call this R1 and this R2, and you can say that R1 divided by B1, or because in this case it was only one voltage source, so B over R1 plus R2 is going to be a current. It's going to be the current at t is equal to 0, right? At t is equal to 0, so we use this in order to find that, right? So at t is equal to 0, so we do I of 0 is equal to 10, right? Is equal to 10 over what? Over what? It's going to be over 4 plus 6, which is equal to 10 over 10, which is equal to 1 amp. Okay, so it's equal to 1 amp, right? That is the current at that moment. Now, so at the moment when t is equal to 0 and nothing has happened yet, this system has some current, right? But this was acting like, because at that moment, it was like fully charged. It's acting like it's nothing there, right? It's just acting like an open source. Now after some time, right? After some time, right? After we found the current, right? It started in a time equal to 0. If t is equal to 1 second, it's going to be discharging and discharging and discharging until that totally goes away, right? Discharges. And it's amazing, amazingly enough, that when you have a capacitor and you disconnect it from the circuit, don't even touch the capacitor just immediately, because even though it's disconnected, you will get zapped with electricity. It happened to me actually once already. So we found the current, right, at t is equal to 0, right? Now we need to find do the rest of the analysis. Okay, so now we're looking at, let's say for example, at this, okay, so let's do some analysis. At t, okay, so at t is less than 0, at t is less than 0, technically at that moment it's going to basically, this is acting like an open circuit, okay? Because we have not get to that point yet. T is less than 0. At t is equal to 0, it's still the steady state. It's still the steady state, right? Because nothing happened yet at that moment. Now at t is greater than 0, right? At t is greater than 0, what's going to happen here? So at t is greater than 0, when somebody has flipped the switch, right? And this is just a long time, this is a little longer, right? At the instant, it's like nothing happened. But when this t is increasing, now you're looking at a circuit like this. So you're looking at just this piece to be isolated. So you're looking at something like this. So you're looking at just the capacitor, and you're looking at the inductor, and you're looking at the other inductor, the other side, and the other resistor, and you're looking at something like this. Actually, okay, so like this. Now, what is going on over here now then, right? So if this is isolated, that means that it's acting like a little, the source has been disconnected, totally disconnected. And this is acting like a little on unit, but eventually it's going to discharge. Eventually it's going to have to be discharged, right? So at that moment, as you can see that the resistance are this resistance right here. Actually, I actually put this. It was supposed to be a resistor. This 3 ohms in this actually 6 ohms, right? Because this can be shorted to a single wire like this, right? And this also, right? It can be just seen as something like this. They simply are in series, right? And this guy is equal to 9 ohms. 9 ohms, right? So 9 ohms. Okay, so now, but then, just you can actually make it like this now. And instead of having something like that, you make this 9 ohms, and then you put back the inductor there. You put the inductor back there, and you put the capacitor back, right? And it look like this, right? So this is 0.02 farads. Okay, so now, we have, and this is ohms. Now we're looking at the like independent system because I've been separated, but at the moment, like again, it's going to be open for a long time. Then it's going to be discharged, and you can actually prove that, in the lab, and you will see that it works very nice. Okay, so now in this case we have in the case of alpha, right? So in the case of alpha, now we have alpha, right? So we have alpha to find the whether it's a first case or second case, right? We doing that type of analysis right now. So we have R is equal to 9 ohms, right? And so at that point, what we do is the following. So let me just clear this up a little bit. So okay, so let's do it. So let's do alpha is equal to what? Is equal to 9 ohms, right? 9 ohms. 9 ohms over what? Over 2L, right? So remember that alpha is equal to R over 2L, right? So now what is actually the L? L is 0.5 henries, so we can write that as 2 times 1/2, right? And that cancels out, and that is equal to, that is 1, right? So that's nothing but 9 over 1, which is equal to 9. Right? So now that's that. Now, so now we're looking at at omega, so omega, actually, omega naught is equal to 1 over the square root of LC, which is LC is equal to what? It's going to be equal to 1 over the square root of L is 1/2 square, right? And then Z is 0.002 square, I believe. Yes. So when we do that, we're going to have the following. We're going to have 0.5 squared plus 0.02 squared, right? And then, actually, no. 0.5 squared times 0.02 squared, and then you take the square root of that, right? And you divide 1 by that, and it's equal to 100. So this is equal to 100. Okay. Now this is what this is, right? Now, okay. So let's see. 0.02 squared times 0.5 squared. Okay. Now, then take that into the square root of that, and then divide 1 by, it's 100. That's interesting because the book got 10. Maybe they did some type of conversion, but that doesn't make a lot of sense. But anyway, so it is what it is. Maybe the book is right, maybe I am wrong. But when I do the square root of this and take the answer of this and divide it into this, is equal to 100. So now, in that case, unless they put something else, let me see. 0.5 Henry, 0.2 Farads. Nope. That's what it is, and that's what I have. So, okay, so the bottom line is that this one, it is 100, and because they did 50 over, that's not right. So 1 divided by, well, yeah, they convert it into a fraction. Does that make any difference? Let me do it. Just do that, just to see. Okay. So they did this. So they did this. So 1/2 times 1 over 50, right? 1/2 times 1 over 50. Okay. So let's do it. So 0.5 times times 0.02. 0.2. Right? So, same thing. Then I take that, well, it's the same exact thing, whatever. It doesn't make any difference. I think the book is wrong, but anyway. So, take that, multiply it together, you got. So, this one is equal to 1 over, according to the book. Okay, so let's do this. 0.01, right? And then 1 divided by, yes. Okay, never mind. Book is right. That book is right. Okay. So technically this is 10. Okay, cool. We found that out. Okay, now let's do. Okay, so that is this, right? Now we know that now the S1 is equal to minus alpha, right? Plus or minus S1, you can say S1 comma S2 is equal to omega naught squared minus alpha, nope, at the reverse, is alpha squared minus omega naught squared. So now if you think about it, right, so what do we have? We have that omega naught is actually greater than omega naught is greater than alpha, right? Because alpha is equal to 9, right? So now what we do is simply, so S1 is equal to minus, right? Minus 9, right? Minus alpha. And then using the plus sign, we can say that minus 9 squared minus 10 squared, which is equal to minus 9 plus the square root of 81 minus 100, right? So when we do that, we know that this is going to be imaginary number, right? So we have 81, right? And we have a minus 9, but we have a plus 9, right? A minus 9. So it's going to be equal to minus 9 plus. This is going to be imaginary, right? So it's 9, it's negative 9. We cannot take the square root of negative number, so that becomes J9. Okay, so we have the first one. Now let's do the second one. So now we know that right here we have a case already. We can actually analyze that we have what is called an underdamped case, right? So we have an underdamped case, even though we have not found the other one yet, but we can actually start seeing that, right? So now let's do this. So okay, at t equals 0, okay, at A, I current is equal to 1 amp, at t is equal to 0, right? So we need this little thing right here. Okay, so now let's do S2, right? So S2 is going to be the following. S2, so S2 is going to be equal to S2 is going to be equal to alpha. It's going to be minus alpha still. So minus 9, right? Minus, right? Now we're doing the minus because we already did the plus. Now we're doing the minus. So in the minus we have a 9 squared minus 10 again. So in this case, it's going to be the same thing, right? So basically, we have another one. It's the same thing. So, but just with different signs. So it's going to be 9 minus. It's going to be minus 9j minus 9j. But we normally write it like this. So it's easy to get messed up. It's good. It's a good habit to get it like this in this form, j 9 or whatever, but put the j first. Okay, so in this case we have yeah, so technically after we do the math right here. So it's negative. It seems like they have S1 and S2 as 4.359. Yeah, and the reason why is because technically this is not. I mean, this is not 9, right? So you got 81, right? So 81, this is 19. So 81, this is 19, right? So with that being said, right? So taking the square root of that number, taking the square root of okay, this is 9, right? So let me correct myself right here. So this is actually 9, but this is 19. This is 19, right? But after you take the square root of that, which in theory not supposed to take it, but if you do it, and you still did negative, you have a j in there. So after you take the square root of this, let me do a step by step. I don't. Okay, I don't want to confuse anybody, right? So, okay, so if I do the square root of this part over here, right? So I got a 9, right? And then I got a plus in there. And then inside, I got minus 19, right? That minus 19 turns into, this is 9 plus 4, 3, 9, something j. It's a little more than 4 because it's higher than 16, right? So 3, 5. Yeah. 359, right? And this j. So that is the values. So if you want to do more correctly, that's the way to to be close, right? A close approximation. So it's negative 9 plus 4, 3, 5, 9, right? And this is j. And it's going to be the same thing. It's going to be the same thing for the other one. So it's going to be like this. So basically it's going to be like this. So S1, S2 equal negative 9 plus or minus 4, 3, 5, 9 j. Okay, so that is the value which will tell us that it is an under-damped system. Now we can go deeper into the analysis and try to to find other for example, we can find the angle from here, right? So we can take the inverse tangent of this, right? This is considered the real number. This is the imaginary number. So it's sine over cosine. So we'll be able to find the angle of this is the sine over the cosine, and take the inverse of that. The inverse tangent of that will find the angle. But so now let's say that the initial condition for that was the initial condition is 1, right? At t is equal to 0, right? Is 1 amp, right? Initial condition for the differential equation. Then we can actually, find the current at 1 second. You can increase it to 1 second and so forth, but we're not going to do that at the moment. We will do that next time probably. Thank you for watching, and I see you in the next video.